The first lecture of Chapter 3. Chapter 3 covers everything about bonding and chemicals equations. So today we are going to look at ionic compounds. So chemical bonds are forces of attraction between atoms. And so we have two different types of bonds. We are going to talk about ionic bonds, which are when electrons are being transferred between atoms. And this is when one of the atoms becomes positively charged, and the other one becomes negatively charged. That positively charged one has lost an electron that we were talking about before, and it gave it essentially to the one that is negatively charged, the one that gained an electron. So that electron is being transferred from the positively charged metal to the negatively charged nonmetal. So this is, like it says, it's generally found when a metal atom bonds to a nonmetal atom. That metal gives an electron to the nonmetal. And then covalent bonds are when two atoms are sharing some of their electrons. And this is generally found when nonmetal atoms bond together. Today we're going to focus primarily on ionic bonds. And this would be like something like sodium chloride that you're all really familiar with. And then covalent bonds would be something like water. So ionic compounds are usually composed of cations and anions. So cations are typically a metal, and anions are usually one or maybe more nonmetals. And these metals and nonmetals are bound together by ionic bonds. And so here, this is a crystalline structure over here on the right. We can think of this as being sodium chloride. And we'll talk about how we know which ones are which later, but the sodium are the little purple ones, and the chlorine are the larger green ones. And you can see that they are on a 1-to-1 ratio. For every one purple sodium, there is one green chlorine. And so this is called a formula unit. This is the lowest common ratio of those two atoms in that compound. Okay, so that's what it's talking about here on the second bullet point. Formula unit is the smallest electrically neutral collection of ions. And so this is just showing a ratio. As you can see, this big, huge salt crystal, there's more than one sodium and more than one chlorine. And it can be as, as many or as few as, the size of your salt crystal. So this NaCl is just telling us the ratio of sodium to chlorine. For every one sodium atom, there is one chlorine atom. And then this, right, this is, we know this as table salt. But the word salt in chemistry doesn't just refer to sodium chloride. It's not just talking about table salt. It's used to refer to ionic compounds in general. So if we're talking specifically about table salt, we'll say table salt or say sodium chloride. But if you hear the word salt, it just means an ionic compound. And it's an ionic compound that's not acting as an acid or a base. So just some neutral ionic compound. So molecular compounds are usually composed of two or more covalently bonded nonmetals. So the bonds in them we call covalent bonds, and then as a whole we call it a molecular compound. And so we have, water or dry ice, propane, but unlike what we saw in the ionic compounds where it's telling us a ratio of just some big, huge salt crystal, right? When we say H2O, we mean there are two hydrogens and there is one oxygen, and that is it. It's just this one molecule here. And then if you had another water molecule, it would be another hydrogen bonded to another oxygen and another hydrogen, right? But it's these, the water molecules aren't going to be bonded together. So it's not a ratio really like we were seeing in the first one, right? In that ionic compound, it's not a formula unit. It's telling you what the entire molecule is. Okay, so slightly different. So we have 7 elements on the periodic table that exist in nature as diatomic elements. And so the way that we are going to remember these is kind of a silly little thing, and it's Hofbrinkel. So it's hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. There are other ways to remember it. Some people remember it as Brinkelhoff. Some people remember it as like the backwards 7 plus hydrogen. No, I guess not a backwards 7, it's a forward 7. But either way, however you want to remember that, you need to know the 7 diatomic elements. So when they are in nature, The term diatomic means that they exist as like H2. And you would know this, right? You guys have all heard O2 as oxygen. Because oxygen can't float around as a single atom, it will always form this double bond and it will float around as O2. Same thing with hydrogen, floats around as H2. So for all of these 7 diatomic elements, anytime you see them by themselves, they're going to get a subscript 2 because there's always 2 of those atoms bonded together. We have a couple other elements that exist as polyatomic molecules. I'm not so much concerned with you knowing these, but phosphorus is P4 and sulfur is S8. So if you see those, they won't exist just as P or just as S. They will typically exist as P4 and S8. But more important that I care about, you must know those diatomics. They're going to show up all the time. Okay, a little bit about ionic versus molecular. So like I was saying before, molecular, they are individual molecules. So if I say C3H8 for propane, that means there is one molecule of C3H8, and then there's another molecule of C3H8, and another molecule of C3H8. But when we have something like table salt, where it's NaCl, that's telling you the ratio. For every 1 sodium, there is 1 chlorine. But it could be as big or as small as, you know, the salt crystals are. So it could be a bunch of sodiums and a bunch of chlorines, but for every 1 sodium, there will always be 1 chlorine. Okay, I want you to go ahead and pause here and classify each one of those as an atomic element, a molecular compound, or an ionic compound. And I have a hint for you at the bottom. Atomic elements, when we say that, those are elements that exist as single atoms. And then molecular elements are those that exist as bonded atoms, like those diatomic molecules from the earlier slide. So go ahead, pause, and then when you're ready to know the answers, unpause. Okay, let's go over this. So aluminum is just by itself, so that one is an atomic element. Aluminum chloride is made up of a metal and a nonmetal. So aluminum chloride is an ionic compound. Chlorine, Cl2, is a diatomic molecule, so we would call this a molecular element because there are 2 of them. Acetone, all of these, carbon, hydrogen, and oxygen, all of those are nonmetals, so that is a molecular compound. Carbon monoxide, also both nonmetals, so that's going to be a molecular compound. And then cobalt is a single element just sitting by itself, so that is an atomic element. Okay, so before we talked about charges of some of these really common groups. So like all of the alkali metals in group 1, they will all have a 1+ charge. And all of the alkaline earth will have a +2 charge. And all of these halogens will have a 1- charge, right? These will all have -2, -3. Those are really predictable elements. Oh, and also aluminum here, that +3. So those we will always know, we can tell based on their group what their charge is, which is great. There are some atoms and elements that are not as easy to predict their charge, and some of them form multiple charges. For example, chromium here. Chromium can be either a 2+ or a 3+. And iron can be either a 2+ or a 3+. Zinc can, only be a 2+. Copper can be a 1+ or a 2+, right? And so these are not as easy to predict and don't really follow a pattern, or not one that's easy to see. So you have a document on Canvas that shows you which of these you need to know and you need to memorize. So, and they have different names, like iron 2+ is called ferrous, but iron 3+ is called ferric, and you need to know the difference. So you need to know what charges they can form. So like iron can form a 2+ and iron can form a 3+. And then you need to know the names that go along with those charges. So when iron is a 2+, it's ferrous. When iron is a 3+, it's ferric. And so there's a sheet. It has polyatomic ions, and then at the bottom it has these elements that have variable charge. And so you need to start memorizing those. My recommendation is to make flashcards. That is the easiest way to go about this. There are a lot of them. Start memorizing them now, because as soon as we get to that nomenclature quiz that's coming up, you are going to need to know all of these elements and their charges. Like I said, these ones, these are easy to remember. They follow a pattern: 1 plus, 2 plus, 3 plus, and then skip 3 minus, 2 minus, 1 minus. But these ones down here are the ones that are exciting. And there's more of them on that sheet. Don't you worry, this isn't all of them. You need to go find that sheet and start memorizing. So this is just, some more of it. There are some transition metals, if you saw on the previous slide, and I'll point them out to you here. It's zinc, silver, and cadmium. Those transition metals do not have variable charge. Silver is always a 1 plus, zinc is always a 2 plus, cadmium's always a 2 plus. And one way to help you out is that this is 1B and this is 2B. So that's how I remember that silver is a 1 plus and zinc and cadmium are a 2 plus. But be careful with that because, copper and gold can form variable charges. One of them is a 1 plus, but the other one's not. So just, if that helps you, cool. If not, find a different way to memorize them. And so these are the ones that are not variable charges. These are the ones that are always a given charge. And so, just memorize the pattern for those guys. Okay, so how to write the formula for ionic compounds. So if we were going to go through and write the formula for aluminum oxide, first thing you're going to do is write the symbol for the metal cation and its charge. So we know aluminum is one of them that does not have a variable charge. Aluminum is always going to have the same charge, and it is always going to be a 3 plus. Okay, so aluminum, always going to be a 3 plus. So then we're going to write the symbol for the nonmetal anion and its charge. Again, oxygen is not one that has a variable charge, so oxygen is always going to be O2 minus. And just on these guys, the number needs to go before the charge. If you write the charge before the number, that means an oxidation state, which is something else, and we will cover that later. In Chem 1, we start to be a little bit picky about these kinds of things, so make sure you put the number and then the charge. So there we go, we have Al3 plus and O2 minus. So then what I like to say is that we will circle and switch. We're going to exchange these subscripts. So the 3 is going to go to the oxygen, and the 2 is going to go to the aluminum. And then you'll get Al2O3. And so you may have learned a different way to do this, which is totally fine. If you already know how to make ionic compounds, great. But this is a really easy way to just see see what they should be. You're just trying to find the lowest ratio in which they cancel out. So in this case, it's every 2 aluminums to 3 oxygens. My apologies. If we were doing something like sodium chloride, sodium is always going to be a 1 plus, and chlorine is always going to be a 1 minus. Since these both have a 1 plus and a 1 minus, like they're both 1 charges, we don't need to do this whole circling and switching step. We just mush them together. NaCl. Okay, it's only when the charges are different, like 3 and 2, then we're going to do this whole switching step. So let's try this. Potassium ion with a nitride ion, a calcium ion with a bromide ion, and an aluminum ion with a sulfide ion. So go ahead and pause, try and write the formulas, and then when you're ready, unpause and come back and see the answers. Okay, going through this. So potassium, and I'm going to write these down at the bottom. So potassium is K plus, it's a 1 plus, and nitride is N3 minus. Because we have a 1 versus a 3, we have to do the circling and switching step. So the 1, that imaginary 1, would go over to the nitrogen, and the 3 is going to go to the potassium. So we write K3, N, and we would write a 1 after the N, but we don't write 1s. Calcium with bromide, so we have Ca2 plus, Br minus. So the 2 is going to go to the bromine. Our imaginary 1 would go to the calcium, so it's Ca, we don't write 1s, Br2. Then the last one, aluminum is a 3 plus, Sulfur is a 2-. So we send the 3 to the sulfur and the 2 to the aluminum. So we get Al2S3. And again, we did the circling and switching for each one of these because all of the numbers were different. If we had something, say, like calcium oxide, where we had Ca2+ and O2-, because they are both 2s, we don't do the circling and switching, we just mush them together because they exactly cancel out. So we would have CaO. So you only do the circling and switching step when the charges are different. Okay, so when we're going to name these, if we're naming binary ionic compounds, and binary just means there are 2 different elements, so like aluminum and oxygen, then we are going to write it in the following form. We leave the metal name alone, and we change the non-metal to end in IDE. So if we had something like Al2O3, the name of this would be aluminum, and we leave aluminum's name alone, so aluminum and then oxide, so that oxygen changes to end in IDE. So this is aluminum oxide. So instead of being oxygen, it becomes oxide. And that's it. So to name these, and I'll just go through these, you could pause if you want, but essentially, remember the first element is going to stay the same. The second element, we're going to change its name to end in IDE. So the first one would be zinc nitride, and then we have barium fluoride, rubidium fluoride, and sodium bromide. And you'll notice that none of these need any kind of prefixes or anything like that, and it doesn't matter for the name what these numbers on the bottom are. Okay, that doesn't matter at all when we're naming ionic compounds. When we get to naming molecular compounds, then those numbers on the bottom matter when we're doing the name. But for ionic compounds, the numbers on the bottom don't matter. We're just looking at what the elements are. We name the first element as its name. The second one changes to end in IDE. So here we have our metals of variable charge that I was talking about earlier. And these are, like I said, some of them. There are more. But we have things like chromium, and so there are 2 different names for chromium, well, there's really 4 different names because we have chromium 2+ and chromium 3+. But so like for chromium 2+, we can name it 2 different ways. We can name it chromium 2, right, and we put the Roman numeral in parentheses after the name, and so that would be their stock system name. And then we have the older name, or the classical name, which would be chromis. Okay, and I want you to know both of these names for all of these elements. And make sure you look on that sheet, like I said, on Canvas. There are more of these. Okay, so you're going to need to know what charges they make, and then both names for those charges. So you need to know like chromium 2 and chromis, or chromium 3 and chromic. Okay, because I may ask you to name it one way, I may ask you to name it with the stock system way, which would be this one. Or I may ask you to name it with the classical way, which would be this older name. We don't really use the older name as much, but it's really good to know because sometimes it shows up on chemical bottles, especially like really old bottles. So let's figure this one. Determining the charge on a cation with a variable charge. So this is just how the font came out. This is gold sulfide, right? Au2S3. We need to figure out what the charge of the gold is, because like I told you, gold can have multiple charge, right? So we need to figure out, okay, which one is this? And this is actually, gold is actually not on this table. So that's showing you, right, that there are more of these. So the first thing you're going to do is figure out the charge on the anion. So sulfur, we know. Sulfur is always going to be a 2- because it's in that 6A group. Since it's always going to be a 2-, you can think about, we know that this 2 came from sulfur if we were to like uncircle and switch, right? So if you think about that, then you know that that 3 is coming from gold. So that's one way to do it, but I have these steps to figure out a different way, okay? So you can figure out the total negative charge. If you don't want to do this uncircling and switching thing, which is usually what I do, but you can figure out the total negative charge. So we know that there are 3 sulfurs, right? Because of this 3 down here at the bottom, or down here, there are 3 sulfurs, and each one is worth -2. So there is a total of 6 minus negative charge. And we know that the gold has to completely cancel out that negative charge, so then we have to have a total positive charge of 6 plus. And in our compound here, it tells us that there are 2 gold atoms. So you can take, okay, if there's going to be a total 6 positive charge, and there are 2 gold atoms, then each one has a 3 plus charge. And then you can name it based on that 3 plus charge. Okay, so here's a little more practice. Go ahead and pause here and see if you can find the charge on each of the cations. So on each of the metals, we want to figure out what that charge is. And you can do it in whatever method you like. So go ahead and pause and then come back when you're ready. Okay, for this first one, we have lead and chlorine. We know the charge on chlorine is a -1, right? Chlorine is always going to be Cl-, but that lead is one of them that has 2 different transition states. So lead can either be a 2 plus or a 4 plus. And so we have to figure out which one of the leads we have. So 2 different ways you can do this. Like I said, you can do it the way on the previous slide, where you figure out the total negative charge. So like here, we have 4 chlorines, and each one is worth, each one is worth -1. So we have a total of -4 from that chlorine. And if you'll see, we only have 1 lead, which means that the charge on that lead must be +4. So this is Pb4 plus. But again, you could kind of do that uncircle and switch, right? This imaginary 1 came from the chlorine, and that 4 came from the lead. Either way, however you want to think of it. So here, on the next one, we have chromium and we have oxygen. We know each one of those oxygens is worth -2, right? And we have 3 of them. So there is a total -6 charge on that atom, or on the set of atoms, right? We have a total -6 charge in that molecule. And then we only have 1 chromium here. So since we only have 1 chromium, that chromium must be +6 to balance out all of those oxygens. So we have Cr6 plus. So we can't do the uncircle and switch thing here because, right, this would tell you that oxygen is a 1-, and we know though that oxygen is a 2-. So if you think about uncircling and switching, if that needed to be a 2, then that would make this a 6. So a little bit trickier there. All right, on the last one, we have iron and we have nitrogen. So nitrogen, we have 2 nitrogens with a total, each one has a -3 charge. So we have a total of -6 on that molecule. And we have 3 irons that are sharing that, +6. So if we have 3 irons for a total of +6, that means each iron is +2. So we're getting Fe2 plus. And so figuring out the charge of these cations is crucial because then you'll be able to name the compound. If you don't know what the charge is, then you won't be able to name it correctly because like I was talking about earlier, each one of these, whether it's 4 plus or 2 plus of that lead, right, it has a different name. Okay, so it's crucial to be able to find the charge so you can name it correctly. Okay, 2 different ways to name them. We talked about the classical name, right, which is like if you had chromium, that's like chromis and chromic, or iron has ferrous and ferric. Like this first iron, that would be ferrous chloride. The next one would be ferric chloride. So it's kind of an older way of naming it, but it shows up a lot on stock bottles. So if you're going to actually go into chemistry or going into a science and you buy chemicals, a lot of times they'll say things like ferrous chloride and ferric chloride. They might also include the iron 2 chloride or iron 3 chloride, but you need to know both names. All right, so the stock system names them using Roman numerals. So you're always going to put the name of the atom, the element, its charge in parentheses, and then you're just going to name the anion just the way it normally is. But it's always going to have a Roman numeral in parentheses. So I have Roman numerals there in case you're not familiar with them. But the charge of that cation is always denoted with a Roman numeral right after the name. Okay, and we only use it for cations that can form more than one charge. So don't go around using it for something like calcium, right? Calcium can only ever be a 2+, so we're not going to put like calcium 2 because it's redundant, because calcium's always a 2+. The ones that people get tripped up on are the ones that are in the that are transition metals that only ever have one charge. And so the ones that we don't do this for are silver, zinc, and cadmium, because those always have that set charge. Okay, all other transition metals and a couple of them over in that in the P block will have more than one charge, so then we will denote it with the Roman numerals. Okay, another special type of naming system is when we have polyatomic ions. And so poly means many, and many atoms that are all together and they are charged, which makes them an atom, or an ion. So we have a bunch of different atoms together with a charge, and they're pretty much always going to be anions, except our only cation we're going to work with here is ammonium. The rest of them are anions, but again, a polyatomic atom or ion is an ion that contains two or more elements. And the way that we name this is we're going to leave the name of the cation the same, or with the Roman numerals, however you might normally name the cation, and then you're just going to use the polyatomic name. You're not going to change the name in any way. You're just going to put the cation and then the name of the polyatomic. So here's a bunch of them. You had a bunch on the previous page. You have a bunch here. If you go onto Canvas and see that document, it says ions to be memorized. It has a bunch of polyatomic ions, and it also has those transition metals that we've been talking about. Make sure that you make flashcards. I also have on the second page of that document some hints on how to help you get from hypochlorite to chlorite to chlorate. And so some of these series that you'll see, or like sulfite to sulfate and things like that. But you do need to memorize them, you do need to know the difference, and you need to do it soon. Okay, let's try and name the following compounds. So right now, it would be helpful if you had that ions to be memorized page in front of you so that you can, figure out what the names of these are, unless you already have them memorized, which is awesome. But so this first one, if we were looking at that page, we would name this as sodium, and then we would find this polyatomic ion, and you would see that that is acetate. So you would name that sodium acetate. The next one is lithium, and then this is a polyatomic here, so that is lithium carbonate. And then we have strontium phosphate. Okay, so again, you're not changing anything about the names of the polyatomic ions, you just got to figure out which ones they are, and that is struggle enough for a lot of people. Next bit says write the formulas for the following ionic compounds. So we're going to get some practice on how to write formulas using the polyatomics. Okay, so potassium hydroxide. So potassium is K+. If you go look at hydroxide, that's OH-. And since they are exactly opposite, potassium's a 1+, hydroxide's a 1-, we just mush them together and we get KOH. Let's try the next one, beryllium. Beryllium is Be2+, and permanganate is MnO4-. And so now we have different charges. We have a 2+ versus a 1-. So now we have to do our circle and switch. So that 2 is going to go on the outside of the permanganate. The imaginary 1 will go to the beryllium. So we'll put beryllium, we don't write 1s, and then that 2 needs to go to all of the permanganate. If I wrote it like this, it would look like it was, 42 oxygens, and the 2 isn't going to the manganese there. So we need to figure out a better way of doing it. So don't do that. So instead, we're going to put our permanganate in parentheses. So we're going to do Be, put the entire polyatomic in parentheses, and then the 2 is going to go on the outside. So in that way, we have 2 manganese, and then we'll have a total of 8 oxygen, if you think about that distributing. Okay, let's try the next one, ammonium sulfate. So ammonium is that one polyatomic that I said is positive. So that is NH4+, and sulfate is SO4 2-. So the 2 is going to go to the ammonium, and the imaginary 1 will go to the sulfate. So since that 2 needs to go to the entire ammonium, we need to put the ammonium in parentheses, and then the 2 is going to go on the outside. And then sulfate here does not need to be in parentheses because it's an imaginary 1, and we don't write 1s, so even if we put that in parentheses, there'd be nothing to go on the outside. So we just write SO4. Then last one, calcium hydroxide. Calcium's a 2+, hydroxide's a 1-. So the 2 is going to go to the hydroxide, and the imaginary 1 will go to the calcium. So we have CaOH2, so that 2 goes to the entire hydroxide. I'm going to do one more. Let's do calcium sulfate, okay? I'm just going to write this up here. So if we did calcium sulfate, so we have Ca 2+ and SO4 2-. So since they are both 2s, right? Calcium's a 2+, sulfate's a 2-, they are going to exactly cancel each other out. So we are going to eliminate the 2s, and we're just going to write CaSO4. We don't need to circle and switch because both of them are 2s, which means they cancel out, which means that they're just going to react on a 1-to-1 ratio. Okay, our last topic for today is hydrates. And hydrates are named just like other ionic compounds, except we're going to say how many water molecules are attached to them. So hydrates are these ionic compounds that have embedded water molecules that just kind of get lopped onto the compound. The compound absorbs water and kind of embeds it in the crystal structure. So we would name this, right? They're always going to be ionic compounds. So see, these are all ionic compounds. They're a metal and a polyatomic, or a metal and a non-metal, but they have this water molecule attached, and it's always going to be attached with this dot. So it's always going to have an ionic compound, a dot, and then a number and water. So ionic compound, a dot, number, water. Ionic compound, dot, number, water, every time. And so the way that we do this, we name our ionic compounds just like we were, and then we name how many waters are attached to that ionic compound. So we have the hydrate prefixes over here on the left. These are really useful to memorize anyways because you're going to need to know them when we get to molecular and covalent bonding. These are going to be the same prefixes that you're going to use there, so you might as well start working on them. So the first one, we have calcium sulfate. Hemi is half, and then hydrate. Barium chloride, we have hexahydrate. And then copper sulfate, hexahydrate. Okay, so like I said, you're just going to use that prefix in front of the word hydrate to tell you how many water molecules are on there. And then this last slide is cool, just to show you that it does, when it changes the crystal structure, it can actually change some of the properties of the molecule. So on the right here, this blue one, this would be no water. And you can tell, right, because it's smaller. But when we have with water over here, it's got this gorgeous maroon color. This is probably my favorite color. I love cobalt 2 chloride that's got the hydrate on it. Anyways, that is the end of today's lecture. Start working on ionic compounds and start memorizing all of those ions and all of the polyatomic ions. You have a lot of work memorizing wise. So start, working on it now so that when that nomenclature quiz comes up, because it is coming, you'll be prepared and not scrambling at the last minute. As always, send me any questions if you have them, and I will